So today's lesson is Unit 1 Kinematics, Lesson 7 Vector Scale Diagrams, and let me just zoom in here. Okay, so first, how are we going to talk about vectors in 2 dimensions? How are we going to even say what direction they're pointing in? So here's some different directions. So I have just a Cartesian coordinate system, and I have one example in each of the 4 quadrants. Now, in physics, what we're mostly going to do is compass direction. So what's a compass direction? Compass's direction is when you have north, south, east, and west. So it looks like this: north, south, east, and west. So in our first case, it looks like we have an arrow somewhere in the northeast. Now they're giving this direction right there, which is the angle, which is a certain degree, in this case 40 degrees above our, in this case, positive x-axis or east direction. So whenever we're writing directions, just like before, we're going to use square brackets. We're starting east, so first east, and then we're going to go 40 degrees towards the north, like this. And that's how we're going to write it. Now some textbooks, maybe even yours sometimes, will write it like this. They'll start with north, and they'll say you're going to head north 40 degrees of east. It's the same thing. Okay, I usually do this one because I prefer it. So of course, when you're speaking, you might prefer this one. You get to actually say, go north 40 degrees of or from east. It's easier to understand this word. Let's do another example. This one looks like it's in the southwest quadrant, and it's 30 degrees from our west direction. So I'm going to write, start in our west direction, over here, start west, and then go 30 degrees towards south. So west, 30 degrees south. Okay, this one, okay, it looks like we're starting north, so north, and we're going 30 degrees towards the west. And lastly, this one looks like the angle is starting from east and going 45 degrees towards the south. Okay, so if something is directly 45 degrees, you can just write southeast. When you just say southeast, that means perfectly in between south and east, which would be at a 45-degree angle. Now, RCS directions, I'm going to talk about bearings. So bearing looks at true north. So basically, any angle that you have, you're going to say, or any direction you have, you're going to say the angle from north heading clockwise. And so, for example, if I were to give you a vector like this, you would simply say what this angle is. If I were to give you a vector like this, you would say what this angle is. And you simply say the angle, and it just means clockwise from north. So in this case, it would be from north, well, you'd need to figure out what that angle is. 90 minus 40 is 50, so you're just going to write 50 degrees. That's it, from true north. This one, you'd have to write that whole angle. So from north to south is 180. 180 plus an additional 60. Again, you have to figure that out by, if this is 30, then this portion right here would be 90 minus 30, which is 60. Then you have 180 plus 60 gives us 240. is not very much used in our physics textbooks, but when you start your calculus and vectors course, in the vectors portion, they use Bering's laws. This one here, you have to figure out what that whole angle is. So from north all the way to west is 270. Then you need to add another 30, so that's 330. Finally, this one we have 90 plus 45, so that's 135 degrees. All right then, so moving on, now that we know how to identify or label the direction of a vector in 2 dimensions, we need to figure out how to add them. So what we're going to do, we have a vector. It's just an arrow. The arrow portion we call the tip, and the end of the arrow we call the tail. And what we're going to do is we have 2 vectors, say A and B, and we want to add them. We are going to move them. They should still be the same length and pointing in the same direction, but you can translate one so that the tip of one connects to the tail of the other, like this, right there. And then, this is your starting point at A. At the tail of A to the tip of B, you will draw your resultant vector, the vector that you would get from adding the other 2 vectors. And what we're going to do today is we're going to practice doing that using something called vector scale diagrams. So vector scale diagrams is you write a scale. So let's say I wanted to add, let's create 2 other vectors. Let's create A. A is going to be, let's say, 400 meters east, and we want to add B to it, which is going to be 200 meters north. Okay. We need to draw a scale. So let's say 1 centimeter. Here's my scale. I'm going to make 1 centimeter equivalent to 100 meters. Just like something you would see on a map, right? So then I can take my ruler here, scroll over, and I can draw 400 meters east. So if 1 centimeter is 100 meters, then 400 meters should be 4 centimeters. And I'll draw that completely east, like this. Like that. So there's vector A. There's A. And then connected to the tip of A, I'm going to draw the tail of B. And it's 200 meters north. That means it should be 2 centimeters. Let me just rotate my ruler here. And I'm going to make it, connect it right to the tail, and have it headed north for 2 centimeters, so it will look like this. And then our resultant, which would be C, if we're adding them, would be going from A, from the tail of A to the tip of B, like that. That would be C. This is B. Then we can figure out the magnitude of C, roughly anyways, using our scale again, by taking our ruler, rotating it, and measuring the length. So the length seems to be about 4.5 centimeters. So that means the magnitude is roughly 450 meters. And then if you wanted to figure out the direction, you would take a protractor and you would measure that angle, whatever it is, theta. I'm just going to call it theta. I don't have an image of a protractor. And then you would say it is east, whatever degrees theta, north. Okay, and we're going to practice that. So our practice question then goes like this. Luna walks to Luke's home. by going one block east and then one block north. Each block is 160 meters long. Draw a vector scale diagram and determine Luna's displacement. Okay, so if one block is 160 meters, what I can do is I can say, well, let's make it 40. Make 1 centimeter. You can choose any scale you want, really. Equals to 40 meters. If 1 centimeter equals 40 meters, then 160 meters would be 4 centimeters long. So let's draw that. First we go 4 centimeters east, and then we go another 4 centimeters north because it's one block east, one block north. Let me grab my ruler. So we are going to start by going 4 centimeters east, and then rotate the ruler, and we'll go 4 centimeters north. We'll connect the tip of one vector to the tail of the next vector. And then our displacement then, which is the sum of these two separate displacements, would be connecting where we started at A to where we finished at B. So this would be our total displacement. Okay, so what's the magnitude of that total displacement? Well, we take our ruler, we're going to measure the length. Which looks to be about 5.5 centimeters. And since 1 centimeter is 40 meters, 5.5 times 40 gives you 220 meters. So our magnitude for our displacement vector is 220 meters. Okay, so that's the final displacement, and then you would have to figure out the angle. You can use a protractor, again, to measure that. In this case, I don't really need a protractor because if that's 40 and that's 40, if this is 160 and that's 160, they're both the same length. That's a nice isosceles triangle there, so I know the angle is going to be 45 degrees. Otherwise, you can just use your protractor. And if this is our coordinate system, where this is north and this is east, I can say our displacement is east 45 degrees north. Or since it's exactly 45 degrees north, I could have just said northeast. But I just want to get you into the habit of writing it like this. Now part C says it takes Luna 10 minutes to walk to Luke's home. Find her average speed. Well, first what we want to do is we want to change minutes into seconds, because we write speed in base units, which is meters per second. So 10 minutes would be, well, 10 times 60, so that would be 600 seconds. Find the average speed. Now, speed is a scalar, remember? So your speed is going to equal your distance over time, not displacement. Distance is the total amount that Luna's actually walked here. So our distance would be 160 meters plus 160 meters, which would give us 320 meters. Running out of space, so let's do this, divided by 600 seconds, which gives us an average speed of 0.53 meters per second. And I'm just rounding to 2 significant digits because that's what we have here. Next it says average velocity. Okay. average velocity, okay, is equal to displacement over time. We've calculated displacement with our vector scale diagram. It is 220 meters east, 45 degrees north. All over time. Time is the same, 600 seconds. So when we find our average velocity, 220 divided by 100, 0.37. Meters per second to two significant digits, and the direction of velocity will be in the same direction as displacement, east, 45 degrees north. Now the thinking problem is, how would you subtract vectors? So let's say you had A, just like this. Let's say this is A, I'm just making this up, and this is B. Well, if you wanted to add A and B, you would simply connect B here, tip to tail, and start off at the tail of A and end at the tip of B, and you would get A plus B. But what if you wanted to figure out what A minus B is? If you wanted to figure out what A minus B is, the easiest thing would be to add the opposite vector B. So if this is B, then negative B has the same length, but in the opposite direction. So now what I could do is I can take A, here's A, and I can add negative B, like this. This is negative B, and you would get A minus B. So the easiest way to subtract vectors is simply to add the negative vector.